In this video, I'm going to talk about line integrals, the concept, the key to understanding them, and the derivation of the formula for calculating them. So, a line integral is a kind of extension of the concept of a definite integral that extends at surfaces that behave like a curtain, that is, they extend into three dimensions. The bottom part is something like this instead of just a straight line. So they extend into three dimensions instead of being flat as a wall would be. But the key to understanding them is that they are just a generalized case of the definite integral. A definite integral is integrating over a flat surface, which is the x-axis, while a line integral is more general and can integrate over any curved surface. This means that you can integrate this using a line integral, just not that convenient, but this you can integrate using a definite integral. You need something else. And that's what line integrals are for. So integration over the x-axis is a special case of integrating over a curve. It's a straight line instead of a curve, right? The definite integrals sort of take place when the function we're dealing with is just the green one in the picture. That is, it's a flat surface. It's not like this. It's just a straight line, the bottom part. But notice that it doesn't matter where the flat surface is located, since the area covered is the same no matter where it is. You see, this could be here, or here, or here. But this area is going to stay the same. So now I'm going to derive the formula to calculate line integrals. So here's the setup. There's a curve in the xy plane defined by the parametric equations x equals x of t and y equals y of t, from t equals a to t equals b. There is also a three-dimensional function above the xy plane. Right, this is it. We want to find the area under the curtain formed over the curve up to the function f of xy. This is the curtain. This is the area I'm looking for. So, the area of the rectangle in the curtain is ds, the infinitesimal width, which is not infinitesimal here, but we can imagine it, times f of xy, the height at that point. So this is ds, this is f of xy, this is ds, this is a different f of xy, right? And so on. Because there is a right angle triangle where the hypotenuse is ds, we can express ds as dx squared plus dy squared and all the square root of all that. Okay? Now, this means our integral, the sum of all the infinitesimal width rectangles, will look like this. The area is the integral from t equals a, endpoint number 1, to t equals b, the endpoint number 2. So yeah, the area is the integral from t equals a to t equals b of f of xy times ds. That's the same as the integral from t equals a to t equals b of f of xy times the square root of dx squared plus dy squared. That's from the Pythagorean theorem, right? Because x and y are functions of t, since we parameterize the curve, they vary with respect to t, and we can express dx as dx dt times dt. Same with dy. Because you can imagine it as if it were a fraction, you'd cancel this out. Now, bringing out the dt from the square root and substituting and then bringing out the dt from the square root, what we get is this: the square root of dx over dt squared plus dy over dt squared. Then we substitute into the equation and obtain the following. The area of the curtain we're looking for is the integral from t equals a to t equals b of f of x of t of y of t times the square root of dx over dt squared plus dy over dt squared dt. This is where we stop because it's convenient for substituting information and retaining the curtain area. See how everything is now kind of in terms of t, and that means if you have enough information, you'll be able to compute the area. Well, thanks for watching. I hope you enjoyed and understood this video, and please leave a comment below if you'd like to see a specific topic in the next one.